So today we're very Arkani-Hamed from the IAS, who will tell us about UVIR, EFT-hedra, and the celestial sphere. Nima?
Okay, well, I'm really delighted to be able to join you. I'm sorry I couldn't make the rest of the meeting. I've been having terrible internet problems all week, and I just barely managed to find some place with a stable enough internet access that I can make it. So I definitely hope to be able to watch some of the talks online, because it seemed to be a terrific meeting. So I'm going to be talking about the sort of broad topic related to this meeting, the interesting sort of UV-IR connections associated with positivity, amplitudes, and things like that. And there are sort of two topics that are loosely related. First, it's a story of the EFT-hedron. Now, this is with the Yutin and Jimmy Huang. As many of you know, that this is a paper that's many years in the writing, the fault of which is essentially entirely mine. But it will be out soon, if absolutely nothing else, for very good reason, for which Jimmy is actually on the postdoc market this year. So we'd like to have the paper out for that. So I've given a number of talks on it already, but just to maybe also set some context, I'll sort of quickly review the story, stress what some of the fundamental beef is, the sort of non-trivial, mathematical facts sort of behind it, and to talk about some of the shortcomings of this sort of entire approach. Which will then naturally seg to the second topic, which is thinking about amplitudes on the celestial sphere. This is work in progress, also hopefully to come out not too long, with Monica Pate, Anna Maria Reclario, and Andy Strominger. And of course, this is a beautiful subject that's been developed very intensively at Harvard, especially over the past 6, 7, 8 years. And mostly one thinks about the beautiful successes of this program in terms of telling us something about soft physics, infrared physics, soft theorems, memory effects, and so on. But as I'll stress, thinking about celestial amplitudes is actually an ideal conduit for exploring this UVIR connection. And in particular, if we're thinking about physics of ultraviolet completion. As you will see in a very sort of precise sense, the kind of weakness of the left-hand side picture is complemented by some strengths of the celestial amplitude approach, and vice versa. So anyway, that's the plan. So let's just quickly to set some context. So we're all now used to the idea that somehow locality, causality, and unitarity of the microscopic ultraviolet theory is somehow reflected in analyticity properties of scattering amplitudes and positivity properties of amplitudes. And this direction, literally as shown here, going from locality, causality, and unitarity to analyticity and positivity, this was the direction of the 1960s. So this is what the S-matrix theorists wanted to do in the 60s, is to sort of precisely understand what is going on with, oops, sorry. They wanted to sort of, they wanted to understand how locality and unitarity were reflected in the analytic properties of the amplitudes, to sort of derive the analytic properties of the amplitudes ab initio, and they failed to do that. And but enough is known that we can say some interesting things about analyticity and positivity. Now, in more recent years, over the past decade, in a sense, an inverse of this S-matrix program has been pursued by many people, many of my friends and I. And it's really an inverse in the sense that we're no longer trying to sort of responsibly derive what the analytic properties of the S-matrix are, which was a sort of hopelessly hard problem from the 60s. Instead, we're trying to do something more adventurous. We're trying to sort of guess some new kind of questions, some kind of interesting new mathematical structures that live in the kinematic space at infinity, These are loosely associated with the notions of positive geometries for scattering amplitudes. These are for n equals 4 super Yang mills, of the story of the EFT-hedra. In the past few years, we've seen generalizations of this to totally non-supersymmetric theories, scalar field theories, and the story of EFT-hedra, and more recently, being developed over the course of the pandemic, the generalization of that story to all loop orders and all orders in the 1/n expansion. So nothing to do with planarity, nothing to do with supersymmetry in the story known as the cluster-hedra. But anyway, there's some sort of deep and hidden positivity, which gives you as an output, not as an input, locality, causality, and unitarity. In any case, that's the program that's being pursued. Now, something else that in many ways inspired by this that we've seen in recent years is that even in this top direction, there is infinitely more positivity that's actually a consequence of the sort of understood locality, causality, and unitarity than certainly at least I had appreciated ahead of time. So here we are again just starting from the sort of obvious positivities. Why are things positive in physics? Things are positive in physics because energies are positive and probabilities are positive. So that underlying positivity, that again going in this direction, but it turns out there's just vastly more, infinitely more positivity there than we'd appreciated before, and that's what's kind of captured by this EFT-hedra structure. So to me, this is some hint of a link between this surprising kind of extra infinite positivity here and these positive geometric ideas that we've been seeing as the sort of heart, as the beginning of the starting point for an ab initio definition of what the amplitudes actually are. So this connection is still not precise in any sense, but all we can say is that very, very similar kind of ideas show up. In both cases, you end up looking at matrices with all positive minors, and these notions of total positivity and so on play a crucial role in both stories. But the story of the EFT-hedra fundamentally follows just from the obvious positivities that are associated with the positivity of energy and of probability. All right, so let me just give the quick overview of the story of the EFT-hedra. And everything begins from the dispersive representation of 2 to 2 scattering amplitude. So I'm going to imagine a process AB goes to AB. To begin with, imagine that we're just integrating out heavy particles. We're ignoring the extra running of higher dimension operators in the low energy theory coming from massless loops. So this is remember, the idea is that we want to sort of constrain higher dimension operators. And if there isn't a weak coupling in the underlying theory, the whole notion of higher dimension operator is ill-defined because the running contribution at low energy sort of dominates everything you get. If there is a weak coupling in the high energy theory, if it's the G string in string theory or a 1/n or anything like that, then there is some approximation just to begin with where we integrate out massive particles. And so the amplitude has a region around the origin where it's analytic, and then it has some kind of singularities, poles, branch cuts, or something like that, corresponding to the S channel and the U channel. And then there's some standard arguments that tell us if there's a gap in the spectrum, there's no gravity, there's no long range forces, then from assuming analyticity in T, so if we fix T to be small compared to the gap, that avoids funny singularities in the S-plane that are associated with anomalous thresholds. So if we say that T is small enough, then assuming the gap, the amplitude is bounded by S log squared S, it's a famous Poisson bound, which has a simple derivation assuming analyticity in T, in particular assuming that we can continue from T slightly negative, which in the physical region, to slightly positive, and a very basic assumption that at fixed T, the amplitude is just bounded by some power of S. If you assume that it's just a power bounded at all, then remarkably, assuming analyticity in T, you get this much stronger statement that it's bounded by F log squared S. There's similar arguments if you have gravity. So if you do have T channel singularities and so on, then again, if the underlying theory is a weak coupling, then there are arguments from thinking about the iconal limit of scattering amplitudes or scattering against shock waves that again tell us that the amplitude is bounded at high energies by s to a power that's smaller than 2. And that asymptotes the 2 as t goes to 0. That's in the case of gravity. If we just had Yang-Mills in the UV, the power would be 1. The biggest the power ever gets is 2 with graviton exchange. But in any case, both of these things tell us that in the approximation we're talking about here, where we're ignoring the massless loops in the low energy theory, then the amplitude has this dispersive representation as a function of both s and t. Again, t is fixed, and this is using Cauchy's theorem in the s plane. And so there are some subtraction terms that in principle we don't know that are up to linear in s, and then we have this we have the sum over states produced with some positive probability, spin s states, which are weighted by the Legendre or the Giganbar polynomial of cosine theta, which we rewrite in terms of t. And then we have the usual propagators in the S channel and in the U channel. So, okay, so that dispersive representation is the beginning of the entire story. And you see there are two things that are positive here. M squared is positive, and these probabilities are positive. And so the entire story of the EFT-hedron is to try to figure out what are the implications of the positivity of these two of the masses. That's saying that the energies are positive, no tachyons, and the positivity of probability. What is the implication of that on the low energy expansion of the amplitude? Okay, and so what's the shape of the constraints that we find? Well, if we take this amplitude and we expand it in the effective field theory expansion at low energies, just in terms of monomials in S and T, then if I make a big list of all of these coefficients, so here I've called these coefficients A, D, Q. D is the sort of engineering dimension of that contact interaction, and Q measures the number of powers of T. And you get this big array of numbers, A00, 10, 20, 1121, 31, and so on. So there's a giant array of numbers, and these numbers have to satisfy infinitely many linear and nonlinear constraints. The story that we're all familiar with, the simple story, really sort of going back to the 60s in many ways, but anyway, the story that was discussed again 10 or 15 years ago is, for instance, that some of these leading coefficients are positive, like A20 might be positive, or in other cases, whole infinite series of these coefficients might just be positive. But there's much, much more than simply that they're positive. There are nonlinear constraints between them. For example, that tell you that if you have a dimension 6 operator and a dimension 10 operator, that you can't make the dimension 8 operator too big. There are constraints that are nonlinear involving products of these higher dimension operators. Just by units, they have to be the units of all the terms have got to be the same, but there's infinitely many nonlinear constraints of that sort, which sort of relate in a nonlinear way the things in the rows of this big table. There are linear constraints. In fact, they're all sort of unified in a giant set of constraints that carve out this EFT-hedron, which is just the sort of space, the geometric space where all of this table lives. But just the roughly two kinds of constraints are the nonlinear ones for the rows, and there are linear ones in the column. So all of these things in the column have the same units. So there are linear constraints on all of these variables. And if you, since they all have the same units, all that matters is the ratios between them. So I can think of them as points in projective space. Anyway, these viewed as column vectors, they have to lie inside particular polytopes. And these are what we call the Giganbar Polytopes and their generalization. So again, they would tell you have two operators, they have the same units, and you can't make one of them 20 times bigger than the other without exiting this polytope. Okay, so that's the nature of the constraints. And again, I've given several talks about this, and I suspect a number of you know the basic story. So what I want to do is just sort of summarize what the beef is. So what are the interesting sort of what are the interesting mathematical facts that lead to these nonlinear and linear constraints? So to begin with, let's talk about something very simple. Just go immediately to the forward limit. So something I'll just call S-channel Henkel, and this really illustrates the heart of the nonlinear constraints. So if you like, this is a sort of toy model where I only have things in the S-channel. I've taken the forward limit, and so I have an amplitude that looks like a sum over the spectrum, P over M squared minus S, and I want to do a low energy expansion of it, okay? So that just tells us that there's some constraints on these coefficients AN from being expressible in this way, okay? So, we'd like to figure out, those coefficients have to live inside some space, and we'd like to figure out how to precisely characterize that space. Not just come up with some sufficient conditions, but completely 100% precisely characterize. And the characterization turns out to be the following beautiful thing. You take all these coefficients, A0, A1, A2, you group them into a giant vector to begin with. That's how you would sort of think about them, all the coefficients. But from that vector, you build a matrix. This matrix is called the Henko matrix, and its ij entry is capital A ij, little a of I plus j. So this is what it looks like: A0, A1, A2, A1, A2, A3, A2, A3, A4, etc. for the rows. Okay, so I'm just repackaging exactly the same data about these higher dimension operators. Now the claim is that 1-to-1, these AN can come from an expression that looks like that has the positivity properties that we like, if and only if all the minors of this matrix A are positive. Okay, every minor. So all the 1-by-1 minors just tell you all these numbers are positive, but the 2-by-2 minors, this one, that one, any 2-by-2 minor, any 3-by-3 minor, all the minors of this matrix have to be positive. Okay, so those are an infinite set of nonlinear conditions, and as I say, it's 1-to-1. So those are precisely the conditions that cut out the space. Just as a small aside, if you don't know this as a low energy effective field theorist, as a low energy person, but if someone told you the gap, if someone told you that in the sum starts at some M star, it doesn't start at 0, it starts at some M star, and they told you what M star is, then of course you know more, and then you can again precisely characterize what the space is. And it has the following very pretty interpretation. Let me work in units where I set this gap to 1, M star to 1, just so I don't litter my equations with M star. Then you start off with exactly the same vector, A0, A1, and so on. And then you build this other vector of sort of first discrete derivatives. And then this other vector of second discrete derivatives, and so on. You see, this expression does not make sense if you don't know about a scale M star, because I'm comparing things with different units, with different units in this vector and this vector and so on. But if you know the gap, this expression makes sense. And the claim is that you're in all the constraints 1-to-1 on the coefficients are that the Henko matrix for this vector are positive. That's the usual one we just talked about, but also the Henko matrix for this guy, the Henko matrix for that guy, and all the rest of them also have to be positive. Okay, so if I give a sort of simple example where you don't need any fancy positive machinery to understand what's going on, just the simple Cauchy-Schwarz, in the case without a gap, if I look in the A2 over A0, A1 over A0 plane, I see that I have to be bounded inside this parabola. If I know the gap, then I have a further line in the space given by A1 over A0 minus M star squared, A2 over A0 is positive, and I'm forced to be in here. Since I don't know what M star is, if I lower M star arbitrarily, then of course this line goes further and further up, and I recover the previous picture. Okay, so that's the first set of constraints. If you like, there's some kind of hidden positivity just in the structure of the propagators, which is reflected in these Henko constraints. There's a second set hidden positivity is associated with the Giganbar polynomials, with the Lejeune polynomials. Again, to illustrate the basic point, if we consider an example just of S-channel exchange, ignore the U-channel for a second, then once again, I have an expression that looks like that. Now I'm going to expand in S and T, and so I'll get some expansion with powers of S and T, and clearly the powers of T are going to be accompanied with derivatives of the Giganbar polynomial, Q derivatives of the Giganbar polynomial evaluated at 1. Okay, so this expression just tells me that if I look at the set of all the coefficients of S to the D minus Q, T to the Q, this vector actually lies in the convex hull of all of these vectors. If I take the first Q derivative, if I take the derivatives of the Gegenbauers evaluated at 1, if I make a d-dimensional vector out of them, and I just take this set of vectors for all spins, all possible spins, if I take the convex hull of all these guys, and I learn that this coefficient has got to actually lie inside that convex hull. And there's a beautiful fact about this is the cool fact about the positivity fact about the Giganbar polynomials, is that we can actually predict ahead of time that the shape of this polytope is the so-called cyclic polytope. And the reason for this is, again, a hidden positivity of the Gegenbauers, which is, again, reflected in a certain matrix, all of whose minors are positive. In this case, if you just stack all of these Gegenbauer vectors together for different spins and define this big matrix, infinite matrix G, SQ, which is the Qth derivative of the S Gegenbauer evaluated at cos theta equals 1, so we get this giant matrix. And the claim is that this giant matrix has all of its minors positive. And when we ran into this a number of years ago, when we were first exploring it, we sort of asked around and looked around in the literature, and no one seemed to have seen this statement. In the interim time, in the past 6 months or so, a year or so, we've actually found that this result was known in the 1960s. And it actually arose in the sort of second flowering of the study of total positivity in the 1960s, where people realized that total positivity was intimately related to orthogonal polynomials, orthogonal with a positive measure. So if you have polynomials that are orthogonal with a positive measure, then various non-trivial facts of this sort follow. And anyway, this statement is actually equivalent to one of the ones that was known in the 60s. But in fact, we had also seen that there's much more hidden positivity associated with these Giganbar polynomials, even more than this statement that was known in the 60s, and this even useful for the sort of very general understanding of the EFT-hedra. When you also include the U-channel and you sort of study everything, even more positivity has got to be true. And so we've actually found what seems to be the sort of master statement from which all the positivities that we need follow. And this statement does appear to also be mathematically new. And I'll just mention it just because it's a very simple and striking statement with no obvious proof at the moment, although it's something that we're talking with the wonderful young mathematician, Steve Karp. Anyway, here's the statement. Let's say that GS of X are orthogonal polynomials with any positive measure. So that means that the GSI, GSJ, or GI, GJ, whatever you want to call it, that the integral is delta ij. Then you look at the following peculiar object. So you imagine evaluating, you take S1, S2 up to Sn, and you evaluate them at positions x1 up to xn. Okay? So now take this matrix and look at its determinant. Now, this guy is clearly antisymmetric in switching xi and xj. Also, it has a property that it vanishes if any two of the x's are equal to each other. So it clearly has a factor. This giant polynomial clearly has a factor, which is the product of all the xi minus xj. So if you look at this interesting ratio, this is now just a polynomial in x1 through xn that's actually symmetric in the x's. And the claim is, so now you can think of this as a big polynomial it's a multi-polynomial that's separately polynomial in x1 through xn. Since we have a basis of orthogonal polynomials, therefore, it's natural to expand this guy as a function of each one of the variables in terms of the orthogonal polynomial. So here is the expansion. So you expand this guy as a sum over our orthogonal polynomials, these GS's, and you keep track of the coefficients. The claim is that these coefficients are always positive. As I said, it's a quite non-trivial statement. It generalizes certain facts about the positivity of the coefficients of sure polynomials, if you know what those are. In any case, so that's what I'm trying to, all I'm intending to do here is say there is one underlying sort of beefy fact, a hidden positivity associated. Giganbars aren't special. There's something associated with orthogonal polynomials, but with any positive measure. So the positivity of the measure does matter there. And in any case, so this is still a conjecture, but it appears to be true, and it seems to be the origin of all the sort of positivities that are actually needed in the general story of the EFT-hedra associated with the Giganbar side, associated with the P-channel side of the story. Okay, so that was a sort of lightning review of the ingredients that go into the EFT-hedra, and I want to close with 2 comments before moving on to the story of the celestial amplitudes. So first, I want to talk about a kind of obvious issue with, incidentally, this may be known to people who've worked on the subject more recently than I have, so I apologize. But something that sort of bugged us from a long time ago is that it appeared that the positivities we get from the analyticity and dispersion relations, unitarity, seemed actually always stronger than what you strictly needed for causality. You know, if we talk about the d5 to the 4 theory example, it looks like all you need is the coefficient of d5 to the 4 to be positive, or that the small fluctuations around the in a big blob where you turn on grad phi shouldn't be superluminal, and yet we get much more from the dispersive argument. And the first little comment is that, in fact, causality actually does ask for much more than just the positivity of the d5 to the 4th coefficient, for example. And it's actually useful to think about the old superluminality argument in the amplitude language. Okay, so what is it that we're doing? We imagine we have some blob of a size capital R, and we throw in a phi quantum, a delta phi quantum. And then, of course, we say inside it goes either faster than light or slower than light, so we get a time advance or a delay due to the presence of this blob. Now, how would we describe this? This is what we say in the sort of classical field picture. How do we describe this in terms of quantum particles? Well, we're looking at the amplitude for the scattering of phi off of this blob. Let's look at the S matrix between blob and phi going in with energy E, and the blob basically stays the same, and phi comes out with energy E. But how do I think about that? Well, I think about this blob as a condensate of a huge number of soft quanta with a momenta of order 1 over R. And so if I think about the full amplitude here, it's a sum of many pieces. There's the first piece where it just scatters off 2 pieces, 2 particles. But then I have something where I scatter off more particles, more soft particles in the blob. And of course, the crucial thing, we're now interested in trying to compute some phase for the amplitude, some e to the I delta of energy. And for the delta of energy, we can get the time delay. But this only ever makes sense when delta is large. How is it that delta can be large and can be reliably calculated? That's, naively in perturbation theory, delta can only be reliable when it's small. So you have to go to some special configuration for delta to become large and calculable. And here, that special configuration is indeed the one where k is very, very small, so that the scattering is very forward. And what happens in that case is that these propagators, the 5 propagators in the middle for the hard particle, are 1 over s, and s is the product of k and e. So this guy is very, very small. This 1 over s is very small, and that enhances the size of the correction that we can get. So again, this is just in the particle picture. This is all stuff that's very, very familiar in many contexts in transitioning from classical, so from quantum particle Bose condensates to classical fields. But in any case, if I look at this ladder at large m, where m is a number of interactions, I get a factor of n choose m for all the ways I could choose the m guys out of the n quanta, and then exactly this factor I a k over e to the m, which exponentiates to e to the I delta, which you can then rewrite. This n is fixed by the sort of grad phi squared. The energy fixes n, and when all the simple dust settles, you find that this phase is a of s over s times d phi naught squared over k squared. I don't know why that comes from. So that then tells you that the time delay should be negative. In order to have time delay, that means that the derivative with respect to the energy of this phase shift should be negative. And that tells us that d by ds of negative a over s over s should be positive. You see, if I had a d phi to the fourth term, the s equals 0 part of this expression is the usual positivity that we talk about, but something more is needed. This has got to be true for all s. And in fact, that beautifully follows from the dispersive representation for the amplitude. There's a tacit assumption here, which is that this bubble is not destabilizing the vacuum. So that means that the zero momentum part of the amplitude, the quartic term, if there is one, we're assuming is positive. If it's negative, the whole argument changes, because then inside, you run away, and then we have to talk about how the vacuum is stabilized. But if we assume that the amplitude at s equals 0 is greater than or equal to 0, it could be a Goldstone, it could be 0. If it's not a Goldstone, we want to imagine that the amplitude at s equals 0 is positive. Then going back to our dispersive representation, we can write the amplitude as negative a s of 0, and then here's everything else, which I've written in the dispersive way of just subtracted this term 2 over m squared, just in order to ensure that this thing vanishes at s equals 0. Okay, so that because s equals 0 is the sort of constant term that I've written there. And now you can do this trivial calculation to look at d by ds of 1 over s times this sucker, and quite beautifully, it's positive, manifestly positive. So you see that this dispersive representation of the amplitude actually tells us this stronger statement, dds minus a over s is positive, which is in fact what we need for causality thought about in a little bit more detail than simply what happens in a completely translationally invariant background, which is what we talked about a long time. All right, so that's the first comment, that this extra structure of the detailed structure of the dispersive representation actually does matter for causality. The second comment is about a sort of a big missing ingredient in all of these arguments, which is that all of these dispersive arguments begin by using some fixed T dispersion relations. And that's perfectly fine, but because of this, we can't input, at least in an easy way, in any way that I know how to do practically, we can't input the crucial constraints of UV completion. In other words, the softness of high energy fixed angle scattering in any of these discussions, okay? So one very practical aspect of this, in all sensible UV examples, the contribution to the discontinuity across the cut in the Legendre expansion coming from higher spins is suppressed as you go to higher and higher spin. You can see this at tree level in string theory, where the residues from the higher and higher spins are small compared to what you get from the lower ones. You see it in field theory, where when you look at the discontinuity across the cut, you interpret it as the exchange of particles of higher and higher spin. But again, what you get from higher and higher spin is goes down. That's also a crucial part of the derivation of the Poisson bound. And so those are things that fact that the residues somehow have to go down for high spin is not put into any of the discussions that we've talked about in the story of the EFT-hedra or any of these other approaches that I know of. And yet it's somehow crucial for the physics of UV completion. So that's something which is missing, and which would be great to add, because it would probably greatly constrain what even further constrain what the space of allowed coefficients looks like. In previous talks, I haven't done it here, in previous talks, the story of the EFT-hedra, we show all these sort of nice compact regions where these couplings have to live. It's very non-trivial. You can't make one 20 times bigger than the other and so on. You get these nice, beautiful, compact polytopal regions. And yet, when you look at consistent theories, they still live close to corners of this polytope, close to the corners dominated by the low spins. And again, that's because we have not figured out how to include the physics of UV softness in a sensible way. All right, so let me stop there. How much longer do I have? I forget. Actually, I apologize. I forget how much time I actually had. Was it half an hour?
Nominally 45 minutes.
Okay, great. Okay, terrific. So I have another 20 minutes to go?
Yeah. Well, let's see. You began at about 10 to. So I mean, yeah. Nominally another 10 to 15, but
okay, great. Okay. I think 10, 15 is fine. It's perfect, actually. All right. So now let me switch to the second subject, as I say, is related. It sort of picks up from this point of trying to think about a way to force the issue of UV completion on us. And I want to talk about UV completion and celestial amplitude. Okay, so let me give to begin with, a sort of lightning introduction to the how to think about the celestial sphere and celestial amplitudes. There are many motivations for thinking about the celestial sphere and celestial amplitudes, not least of which is it's one of the most obvious geometric places that you might want to look for a sort of hologram for flat space. The kind of boundary of flat space is labeled in the boundary observable are scattering amplitudes. If we want to think about some kind of holographic theory for them, we want a theory that just lives in the kinematic space that defines the on-shell momenta of the particle scattering. Much of the story that I alluded to earlier, the positive geometries, the EFT-hedra, and so on, is a kind of rather abstract way of finding these combinatorial structures in kinematic space. A quite direct way, a quite direct, more geometric way, certainly more intuitive way, is to just think about where things go when you go out to infinity. And they go to lighting up points on the celestial sphere. So how do we think about that? Technically, it's extremely simple for null momenta, and it's intimately related to the familiar spinor helicity variables. So if you take a null momenta, you can write as lambda lambda tilde. So I can take in Minkowski space, lambda tilde is supposed to be the complex conjugate of lambda with a plus or minus sign depending on whether the particles are incoming or outgoing. So that means that I can write lambda as 1z with some factor and lambda tilde as 1z bar with plus or minus that factor. That factor is interpreted as the square root of the energy of the particle, and z is just interpreted as the points on the celestial sphere that null ray goes to when I think about the celestial sphere as a Riemann sphere. Okay, so that's it. So if you have any expression for amplitudes written as a function of lambda and lambda tilde, which is the way you talk about null momenta, it is immediately an expression on the celestial sphere. Okay, so that and if we think for a second about how Lorentz SL2 acts, Lorentz SL2 just takes this full vector little lambda, let's say, and it multiplies it by a general 2x2 matrix, which we can then bring back to the form with an overall phase and some rescaled omega prime and z prime, where z prime is given by this Mobius transformation, omega prime is given by cz plus d mod squared omega, and I get this phase, which just reflects the action of the little group. So Lorentz transformations act nicely on the celestial sphere. They just act as ordinary conformal transformations, Mobius transformations on the celestial sphere in 4 dimensions. Okay, and once you start thinking in this way, it becomes natural, if you're thinking about scattering amplitudes, not to scatter not to scatter momentum eigenstates, which is what we normally do, but instead to scatter boost eigenstates. And that's really the non-trivial idea of thinking about celestial amplitudes, is that we're not scattering ordinary momentum eigenstates. We're going to instead look at these states, call them delta z. They're labeled by, in other words, ordinary states are labeled by lambda and lambda tilde. So you can think about the ordinary states as labeled by the energy and labeled by Z. Okay. However, instead, we're going to talk about boost eigenstates that are related to the ordinary ones in this simple way. I just integrate over all the energies, d omega over omega, omega to the delta times omega times the state, the plane wave state, the momentum eigenstate, omega Z. Now, what is the point of this? The point of this is that now this state transforms as nicely as possible under Lorentz transformations. Under SL2C, delta Z transforms by this overall power out in front, and Z gets replaced by its Mobius transform. In other words, this state transforms exactly like a this state transforms exactly like a primary field in a conformal field theory on the sphere. Notice that this conformal symmetry on the sphere is nothing other than Lorentz symmetry. Okay, so those are the interesting states to scatter, and notice that these are literally eigenstates of boosts in the Z direction. If I do a boost in the Z direction, then Z stays the same, and I pick up this factor up. I pick up this factor out in front. Right. So you want to sort of physically think of these as not scattering momentum eigenstates, but scattering boost eigenstates. That's what we're interested in doing. All right, so how do we think about scattering amplitudes for boost eigenstates? Well, they're just this transform. They're just this transform. Here are the ordinary momentum amplitudes, and which are a function of energy in Z, and I'm going to transform them to something as a function of delta in Z in this way. So it's just a Mellin transform of the ordinary amplitudes. Now, when you work on the, what we've done here is manifest the action of boosts, is scatter states that transform simply under boosts. What we normally do is scatter states that are, that transform simply under translations. So normally momentum conservation is a triviality. It's just a big delta function for momentum conservation. Now in this story, momentum conservation is non-trivial. It puts some constraints on, it puts a more interesting constraint on the variable. Okay, so let's talk about all of this in the case of 4-point scattering. So if we have 4-point scattering, as familiar, the SL2C symmetry tells me that I can only have dependence on the cross ratio of Z1 minus Z3, Z2 minus Z4 over Z1 minus Z2, Z3 minus Z4. There's only one variable, Z and Z bar. So in principle, I have Z and Z bar. But when I do this transform, momentum conservation tells me something interesting. Let's say I have 4-point scattering. Momentum conservation actually puts a constraint on where these points can be. And the reason is that for 2-to-2 scattering, the entire scattering process takes place in a plane. So here I've drawn the plane in which the scattering process takes place. Notice that this plane pierces the celestial sphere, and therefore the 4 points have to lie on a circle, the circle that you get by slicing the celestial sphere with this plane. So that means that the amplitude on the celestial sphere, the boost eigenstate amplitude, is 0 unless the 4 points lie on a common circle. So unless the 4 points are co-circular, and that's a very sort of classic fact that the condition that 4 points are co-circular is that the cross ratio Z is real. So that means when you do this, and you see this, of course, explicitly, if you put in the momentum conservation delta function here, you see that when all the dust settles, you get a factor of delta of Z minus Z bar that's sort of precisely reflecting the simple geometric fact that because of momentum conservation, the 4 vectors lie in a plane. All right, so when all is said and done, then we get an incredibly simple expression for 2-to-2 amplitudes in Mellin space. And I apologize, this should be a function of delta I, not Zi. The amplitude as a function of delta I and Zi is some universal factor that has the helicity dependence in it. The helicities of the external particles, this factor that forces Z to be real, and then everything else is simply a Mellin transform of the good old-fashioned 2-to-2 scattering amplitude. at fixed angle. Okay, so z here is related to cosine theta, just as z is negative 1/2 1 plus cos theta. Omega is the center of mass energy, and so the celestial amplitude is up to these factors up front that we're not going to talk about, is literally just a Mellin transform of the fixed angle amplitude. Okay? This variable beta is just the sum of all the deltas. Okay? So I'm not going to write all the deltas anymore. I will just work in terms of beta. All right, so that's what we've so we're talking about boost eigenstates, and the scattering of boost eigenstates is simply related to ordinary amplitudes that we know and love by a Mellin transform. And now we're going to be studying some properties of that Mellin transform to learn some interesting things about ultraviolet physics. And as I said, the study of celestial amplitudes over the past number of years has already clarified, unified, and revealed many beautiful aspects of infrared amplitudes, soft amplitudes, and so on. And actually, in our paper, we're going to talk about we will discuss the sort of universal exponentiation of infrared divergences and so on that, again, we're familiar with from ordinary amplitudes as an extremely beautiful interpretation related to some things other people have said as well. But anyway, it's a very beautiful interpretation on the celestial sphere. And in particular, there's a totally canonical way of stripping off the infrared divergences to be left with things that are totally sensible. Again, you would expect that for photons and gravitons. You'd expect that as sort of follows from analogous things in momentum space, but as a very pretty interpretation on the sphere. But that's not what I want to talk about, given the limited time that I have. I want to talk about the ultraviolet aspects, and the physical point is sort of totally obvious, which is that if we care about this sort of UV-IR connection, then actually thinking about scattering amplitudes of boost eigenstates is much more in your face, forcing the UV-IR connection on us than the conventional momentum eigenstates. And the reason is that this maximally violates Wilsonian intuition, because the states that we're scattering have arbitrarily high energies in them. And in particular, the effective field theory amplitudes don't even make sense. So here's a very simple example. Imagine we have 2 to 2, I don't know, gravity amplitudes, pions, whatever. A low energy amplitude, m of omega, I'll call it m, not to confuse. These are the ordinary 2 to 2 amplitudes. Let's say they go like omega squared or omega to some power. Okay, well, that's what we get in effective field theory. Well, if you shove that into the Mellin transform, you just get something totally ill-defined, right? You get the integral d omega or omega to the beta plus 2. Okay, it's totally ill-defined. It's a divergent integral, totally ill-defined for any p bigger than 0. And the divergence is an ultraviolet divergence, right? It's coming from omega goes to infinity. So again, obviously what you'd expect. We're scattering states that have arbitrarily high energies, so it just doesn't make sense to talk about the effective field theory approximation for these amplitudes. We have to deal with UV completion from the get-go. And this is a good thing for the reasons that we talked about before. Remember, in the previous discussion, it was hard for us to put in the information about good high energy behavior. Here, for the Mellin amplitudes, even to be defined, we have to have good high energy behavior. And so we can sort of start with that and begin to explore how the physics of UV completion is encoded in the celestial amplitudes, in these Mellin amplitudes. And there's many aspects to this problem, but here I'm just going to talk about the one where this sort of anti-Wilsonian aspect is most in your face. I want to talk about how UV completion is reflected in the analytic structure of the celestial amplitudes in this beta plane. So let me begin with the simplest example. Actually, maybe I'll do a little aside here. Maybe the very simplest example, what if the amplitude was just lambda? Let's say the amplitude was just a constant. Then if I do this, d omega over omega, 0 to infinity, omega to the beta, just times 1, just times lambda. Now, this barely maybe makes sense. If beta was equal to IB, and I put omega equals e to the t, then this would be the integral 0 to infinity e to the I tb, which would be delta of b, or delta of negative I beta. And so this guy I can transform just barely. You see, I get something that's horribly non-analytic in the beta plane. It's got a delta function, delta of negative I beta, but it sort of barely makes sense. So just keep that in mind. So now we're going to do something else. Now we're going to imagine that we are, instead, we have some phi cube theory, some massive particle. So this guy's massive, sorry, mass m, and I integrate it out. And so the full amplitude just looks like 1 over s minus m squared with a coefficient of that lambda is just g squared over m squared. Okay, so coupling g. I've done it that way because at low energies, the amplitude is just minus lambda. But of course, at high energies, it softens and it looks like 1 over s. All right. So let's do the Mellin transform now. Okay, so here's the, in this case, you can just trivially do it analytically. And you get this interesting expression where m is the mass of the particle. I get m to the beta over 1 minus e to the I pi beta. And this guy has an infinite series of poles on the real beta axis. Okay? So let's try to understand why we have these poles. The origin of these poles is extremely simple. I have infinitely many poles in the beta plane, but all these poles at negative beta are actually associated with the low energy effective field theory expansion. Okay? They're associated with the fact that if I look at this amplitude at low energies, I can expand it in some powers of omega squared. And as I'll just review just trivially in a second, those powers, those positive powers of omega squared, gives me poles in beta at negative values. So omega to the 2n gives me a pole at beta equals negative 2n. And the residue on the pole is precisely given by the coefficients of that higher dimension operator, or the coefficient of that term in the expansion of the ordinary amplitude. We also have poles at positive beta for the inverse of that reason. This amplitude has an expansion at large omega in inverse powers of energy, and it's exactly the same argument. Those give me poles at positive values of beta. That's why we knew ahead of time, without doing any work, this expression has to have an infinite series of poles for negative beta. And the beautiful thing is that the residues of those poles are precisely the coefficients of higher dimension operators. And similarly, an infinite series of poles at positive beta. And again, the logic for this is totally trivial. We look at the Mellin transform, and it can have divergences as omega goes to 0 and as omega goes to infinity. So let's look at what the divergences around omega goes to 0 could look like. Okay, what it could look like if I have a positive power of omega here, I can get these poles when beta is sufficiently negative. Okay, so if I make beta sufficiently negative, I get a divergence from this integral. And anyway, this expression, an expression of this sort at low energies will give me a pole at beta equals negative 2n, and similarly up here. If I make beta too big, in the UV, now when the integral goes from omega star to infinity, I'll get a pole at positive value. Right? So the infrared behavior is reflected in the poles at negative for negative beta, integer beta, and the UV power law behavior is reflected in poles at positive. All right, so that's now one thing I want you to notice right away, just to illustrate this extreme anti-Wilsonian business. Notice that at low energies, this amplitude, at low energies, this amplitude looks like a constant, okay? So, but notice that in no sense does this Mellin transform look anything like delta of I beta. They look nothing like each other, okay? And this is exactly the anti-Wilsonian business that I was talking about. In fact, notice that the entire mass dependence just factors out at this overall power of m to the beta out front. Okay. All right. I just got a reminder to wrap up. I'll just be another 3 or 4 minutes, and I'll be done. From here, we see there's actually a radical difference between quantum gravity and field theory. Again, another aspect of how there are these stark differences, which there's no sort of low energy part to run to, which papers over the differences between them. in field theory, as we've just seen, we get poles at both negative beta and positive beta, integer beta. However, in any consistent theory of quantum gravity, there can be no poles at all on the positive beta axis. And the reason is very simple. The amplitude is actually exponentially soft at high energies. If you have strings, that's already true in perturbation theory, but no matter what happens, ultimately the 2 to 2 amplitude is dominated by black hole production and is exponentially small. It goes like something of order e to the minus some constant g Newton omega squared. And so that means that there's no poles at all on the positive beta axis. I can make beta as big as I want, and the integral for large omega will always be convergent. So that's a stark difference of the analytic structure of quantum gravity versus field theory. And this is the analog of the absence of bulk point singularities in ABS, if people are familiar with that story. Another simple fact, let's now, we did a kind of a tree approximation example, but now let's include the whole gamut of log running of the higher dimension operators in the low energy theory. In other words, let's now include all the massless loops, everything that you might have. We know here I've just illustrated the case of just graviton loops, but gravitons, photons, doesn't matter. So any massless loops in the low energy theory. We know that the amplitude gets dressed by all these logarithms, ultraviolet logarithms. Put aside the infrared logs, which are taken care of another way. But they're ultraviolet logs that have the general structure that I've shown here. So we have the sort of contact terms, and they can also be dressed with powers of. They can also be dressed by powers of logs. How is that reflected in the Mellon amplitude? Well, all these logs are simply reflected in the presence of multiple poles at integer beta. In other words, the analytic structure is always the same. You only have poles at integer beta, but you can have double poles, triple poles, higher poles, and those reflect the log running of the higher dimension operators. That's again just trivial fact that if I look at what the singularities in beta can look like, so this A is a stand-in for beta plus whatever else that we can have coming from low energies in this integral. Well, it's just taking k derivatives with respect to what I had without the log, and so beforehand I had 1 over a, and now I get 1 over a to the 1 plus k. So the Mellon transform of something with logs in it at low energies will just give me multiple poles. So we have this sort of nice picture that the amplitude has not just simple poles, but has double poles, triple poles, higher poles at more and more negative beta. And the residue on those poles is directly associated with the coefficients of this low energy expansion, even including the log running of the higher dimension operators in the low energy theory. So I think this is very beautiful. We've been used to talking about the coefficients, these coefficients, with or without the log running, and having dispersive representations for them and so on. But the main reason we have cared about that is that, well, those are what the low energy person sees. Those are the coefficients of the low energy effective theory and so on. On the celestial sphere, these are more canonical objects. They're literally the residues of the poles and of double poles and higher poles of the amplitude. And again, if you have a field theory, you'll have these poles at low energies and some analogous poles at high energies. In gravity, nothing in high energies. Nothing at positive beta. We only have this infinite sequence of poles at negative. Finally, we can, so we know something about all the poles, and there's no other singularities. So we just have these poles in beta. Finally, we can learn something about the large beta behavior. As beta goes to plus infinity, then this Mellon transform is clearly dominated by the large energy limit of the amplitude. And once again, if you have quantum gravity, we know that the large energy behavior of the amplitude looks like that, ultimately because of black hole production. So that is reflected in the growth of the Mellon amplitude. Again, it's kind of cool. The physical, or the ordinary amplitudes, momentum amplitudes die exponentially as we go to high energies, but the Mellon amplitudes on the celestial sphere grow exponentially as we go to large beta, reflecting this the amplitude for black hole production. In the opposite range. So that's in the right part of the complex beta plane. In the left part of the complex beta plane, as beta goes to minus infinity, then it turns out that the amplitude has this universal behavior. Of course, it has this infinite sequence of poles. And at large beta, it's actually m star to the power of beta that multiplies this infinite sequence of poles. M star is the gap to the first massive state. Okay, so at tree level, it would be the position of the first massive particle. At loop level, it would be where the cut begins. At least again, this is in the approximation of ignoring the log running in the low end of U theory. The log running in the low end of U theory would further give us higher poles here. Okay, so but apart from those poles, the important point is that there's just this simple power law behavior that's determined by the lightest particle in the spectrum. Okay, so these are just some examples of how the physics of the ultraviolet is sort of is reflected in a very simple way in the analytic structure in the beta plane. So you might say, what determines this guy? What determines A of beta and Z? We've already seen that the poles in beta are effective field theory, running effective field theory couplings. And again, these poles are, the residues on these poles are exactly what we've constrained by the EFT-hedra. So now on a just more canonical object, just the residues of this nice celestial amplitude are forced to live inside the EFT-hedra. We also know something about the behavior at infinity. Plus infinity is prescribed by black hole physics in the gravitational case. It grows exponentially as prescribed by black hole physics. The leading behavior of beta goes to minus infinity is controlled by the gap. So we seem to know a lot about this. What else is needed? We know what the poles are. We know the behavior at infinity. What else is needed to totally determine the amplitude? And there is still something missing. And what's interesting is that the thing which is missing is so we've sort of hardwired in good UV behavior. Notice that the melon amplitude is the transform of the fixed angle amplitude. Okay, so that's exactly what we had poor access to before, is what happens at fixed angle. And we see that talking about this object, which is the melon transform of the fixed angle amplitude, imports some of the constraints that we got from our previous discussion, which knows about the causality bounds that come from the dispersive representation at fixed t. So the dispersive representation at fixed t tells us something about positivity, which is beautifully, simply reflected in the structure of this celestial amplitude. But it's easy to see that somehow more is needed directly from starting from the celestial amplitude. For example, I can take the celestial amplitude and add to it mu to the beta, where mu is bigger than the gap. Okay? If I do that, then you can see that this is subdominant. It doesn't change the pole structure, obviously, and it's subdominant to the behavior, both as beta goes to plus infinity and as beta goes to minus infinity. If I'm talking about gravity, the exponential behavior of plus infinity beats this guy. Okay, so naively, I could just add this, and it's not changing the poles, it's not changing the behavior at infinity, but there's something very wrong with this. And you can see that because the amplitude back in frequency space would get shifted by a delta function at s equals mu squared. Now, this is horribly non-analytic in S. So obviously, this is not allowed. So what we need to understand is what are the constraints on the melon amplitude that reflect the analyticity, even the very rough analyticity for the amplitudes back in frequency space. And this involves clearly some interesting interplay between Z and delta. It's non-trivial to see the kind of fixed T behavior in the melon amplitude simply because, as I said, the melon amplitude is literally the transform of the fixed angle amplitude. And yet we know that the causality constraints and the dispersive constraints and other constraints have to do with fixing T. So, it would be good to sort of sharply understand how the fixed T statements translate in the story of the scattering of Bootstrap states. But so I haven't done that. I've just sort of shown you how various aspects of ultraviolet physics and even some dramatic aspects of UV completion are reflected in very simple properties of this celestial amplitude. The hope is that, that if we start looking at more examples and we understand better what the rules are, then this will be a setting where it's much easier to think about UV completion for the reasons that we've seen already. We can't, it's sort of forced on us. The UV completeness is forced on us from the get-go. We've already seen these celestial amplitudes tell us a lot about infrared physics, but it's clear that they also know a lot about ultraviolet physics, and so I think it's a very interesting direction to try and understand, both translate things we know and understand better sort of ab initio what the rules are for the consistency of these celestial amplitudes. All right, I'll stop with that. Thank you very much. Sorry for going over time.
Thanks, Nima, for a wonderful talk. Does anybody have any questions?
Hi, Nima. Actually, just a quick one about the celestial sphere amplitude. So do we know actually in the beta plane that those are the only poles? There's nothing in the complex?
Yeah, I think so. I don't have a very rigorous argument, but I'm pretty sure that that's true. Certainly it's true in examples.
Nima, and
in other words, you can look at examples with poles and cots for the amplitude and transform them, and you only ever get poles in the beta. I think the argument is just this simple one, that you just ask where the singularities can come from, and they come from either from omega goes to 0 or to infinity, and it's just that basic argument. Since we know something about what it looks like, so especially in gravity, at infinity, there's nothing. So let's just focus on the IR. In the IR, we know that it's just powers of omega modulated by logs. And that's it. It's because so transforms with powers of omega modulated by logs just give you poles and double poles and triple poles and higher. So that's the argument. And you can explicitly see it in examples too. So that's why I think there's the only thing, the only singularities are poles in beta. However, there's clearly a lot of information in the behavior at infinity. So I gave you one simple thing, which if you look at the leading behavior as beta goes to minus infinity, it's given by m star to the beta, right? Now, for example, if you look in a little bit more detail, there's a power law prefactor in front of that m star to the beta that actually tells you about what the production cross-section is near threshold. So if near threshold, the production cross-section goes like s minus m squared to the q, then you get a power beta to the q out in front of this m star to the beta. Then clearly, if you have, let's say you're at tree level and you had like many particles, then clearly there's something subleading to there's an m1 to the beta, and then there's a subleading m2 to the beta underneath it, and m3 to the beta underneath it, and so on. So it looks like, you know, as you go further and further into the UV, in the conventional sense, it is, I mean, all the higher dimension operators are reflected in the poles. The running is reflected in the higher poles. And then the actual states and their discontinuities and all of that is reflected in the detailed behavior at infinity. Not just that it's falling off in some particular way, but the sort of pattern in which it is falling off. So I think there is no action with branch cots or other things elsewhere. The action is in understanding something about this sort of what the systematic expansion is around infinity.
Nima, are these higher poles related to log running supposed to get resummed and produce single poles at displaced locations?
No. But this is a very special thing about the log running for things like gravity, or for photons where at low enough energies we just have Euler-Heisenberg. In other words, when you have log running with dimensional couplings. When you have log running with dimensional couplings, the thing that you talk about does not happen, because every time you get a log, in other words, you don't get log plus log squared plus log cubed plus log to the fourth and so on, multiplied by something dimensionless. you get omega squared log, and then you might get a higher power of omega because it's coming along with G Newton or some higher dimension operator, right? So the logs don't pile up. And that's why all you get are these, for photons and gravitons or anything where the IR amplitudes are soft, and all you get are these multiple poles. If you repeat the argument for field theory, it's much more interesting. I'm sure, like for Yang-Mills or something, where we have like running of dimension-less couplings, then it's much more interesting, and the phenomenon that you say can definitely happen. So it can happen that all the logs resum when you just move the position of the pole, for example. But that does not happen for photons and gravitons at low energy. It's a simpler story.
But you don't produce any cuts in this amplitude. They stay metamorphic.
Yeah. Oh, you mean, I don't know for a fact what happens in field theory. If I remember in some example, I think I convinced myself, I can't remember. Let me not say. It's possible that these things could pile up and give you a cut. But in any case, it does not happen in this case.
Nima, I had a question about the orthogonal polynomial positivity conjecture.
Yes.
So, besides the usual Legendre or in general dimension Gegenbauers, I mean, this put me in mind of, another set of orthogonal polynomials, that is the spinning Gegenbauers, or the bigger or small d matrices.
Yes, it's true for everything. Yeah.
So but what I'm wondering is every every basis of orthogonal polynomials that's positive with respect to some measure, is this somebody's partial wave expansion for some set of states?
I guess you could think of it that way. Yeah. I mean, you mean, but for external states with spin, or even I don't know. Oh no. I see. You mean if we think of some weirdo combination of spins, can we engineer any orthogonal polynomial?
Exactly.
Is that what you're asking? I don't know. Good question. I don't know. My gut feeling is no, but I don't know.
Nima, may I ask, when you're talking about losing analyticity essentially in quantum gravity, right?
No, we don't lose analyticity. We don't. I mean, I think we don't know exactly what the rules are. I think we know what. Yeah,
exactly what I'm trying to ask about, because once you roll this delta function, whatever, is clearly non-analytical. But
yes.
Of course, I wonder what would be instead, right?
Yes, right.
Right.
Yeah.
But
I think that I would say that, I mean, something that you probably know better than me. But bringing Cole to Newcastle, as it were, that we understand something about we don't even understand the analytic structure in field theory. Okay, I mean that's really a massive embarrassment to me. You want an example of a clear physical problem. It's about the real world, directly about the real world, and we do not know in the year 2020 if someone hands you some amplitude, you don't know how to check if they're right or wrong. You can check if they're wrong. You can see is it not unitary, but it could have some sort of weird glance, and you just have to shrug and say I'm not sure, right? So we don't know. Completely unlike the situation for Euclidean conformal field theory, where we know everything. So for Euclidean questions, we know essentially everything, and it's just a very hard math problem to figure out consistent correlation functions. But for amplitudes, which are intrinsically Lorentzian things, we do not. So first, we don't even know the answer in field theory. But we know some things, and if there's a weak coupling, so one little general point I want to make is that in order to be able to find some constraint on an amplitude, we do need to find some physical situation where the amplitude sort of exponentiates and we can get a large phase. Only when we get a large phase can we sort of conclude that something is right or wrong. And so in the story of the d phi to the 4 and higher dimension operators, it's that you turn on this background, and in the background you can go superluminal, but if you make the background big enough, you can make the time delay as large as you want. In the story of scattering involving gravitons, you have to find you have to make t very, very small, so that again the phase can become large, like when the moon goes around the Earth, the Arkani approximation or scatter off shock waves. You have to engineer a situation where the phase becomes large, and then it's so in your face that we can say something. But what we don't know is what the actual conditions are on the amplitudes. You know, when they're small, they're perturbative. We don't know what they are in detail.
Okay, thanks.
Are there any other questions? Well, hearing none, let's thank Nima again for a great talk, and we can continue the discussion on Slack.
Thanks a lot, guys.
And thanks, everybody, for coming to the UV Meets the IR conference at KITP. It's been a lot of fun.